traffic, experimental 542 Bravo Juliet. We'll be taking runway 29 shortly. There's one side of the runway coming back to center line.
Go if your checklists are complete and you're ready for flight. TC's go.
Controls 1 go.
EP1 go. Batteries go.
Scribe 1 go.
Scribe 2 go.
Limits for flight confirmed. You are cleared for flight.
Copy, picking up.
Hey boys and girls, welcome back to Munro Live. Thank you very much for stopping by to have a look at the future, as far as I'm concerned, the future of transportation. I'm here with JoeBen, and this is Joby, his company. We're going to be talking a little bit about vertical takeoff machines. VTOLs are extremely important in the future. If you ever wanted to have the Jetsons kind of experience, this is step one. So anyways, thank you so much for letting us have a look at your facility. I'm delighted to be here. Why don't you give us a little, I'm looking around, I see a tremendous number of fixturing, things in production, or at least this looks more like production than it does just prototyping. So I'm very impressed. I'd really like you to give us the lowdown on Joby.
Thank you so much. Yeah. Really fantastic to have you here. And so this is our composites final assembly facility. And as you noted, we have a significant amount of fixturing around the facility here. These are tools that we're using to build. We call this our pilot manufacturing line. Where our target is to get to parts for one aircraft a month by the end of this year. And as we go through it, you'll see planes in all different states of construction. So behind us, you see a wing going together, and we have tail fixturing and fuselage fixturing. All of this was developed in partnership with Toyota. And we have an incredible partnership with Toyota. They've been working shoulder to shoulder with us, both here in Marina as well as in San Carlos, which you'll be visiting this afternoon, to really optimize our processes and streamline and use this as a facility to learn the lessons so that we can get the manufacturing processes right as we look to scale to larger and larger volumes over time.
You know, I think that one of the things that I really like to hear more about is how did you come up with the concept? Just give us a little bit more about Joby, how this all came together. Because quite frankly, you know, one day nobody heard of you, and the next day you're getting the biggest single contract for vertical takeoff on the planet. That would be Delta, correct?
So we've got an incredible partnership with Delta, with the DoD, with Toyota, with Uber. So we're very, very fortunate across all the different pieces of our go-to-market strategy to have amazing partnerships. In terms of your question about the background, this was a dream of mine from when I was a kid, to build a better way to get from A to B, and worked on it back in 1993 when I was in college. At that point in time, batteries weren't ready. We were at about 50 watt hours a kilogram specific energy. That progressed through the 90s and early 2000s to the point where we had batteries that had enough specific power for vertical takeoff, but also were approaching 200 watt hours a kilogram. Today we have cells that are over 300 watt hours a kilogram and that also have the power to do vertical takeoff and landing. And so battery technology has been steadily progressing, and that's enabled this new age. And so I formally founded Joby Aviation in 2009 after having dreamt about it and worked on it for many years. Started in a number of other companies that gave me the financial means to kick off what is now become an electric aircraft revolution with recently announced that there were, I think, 1,000 different concepts that people had come up with. So this is very akin to aviation in the early 1900s, where there was like a Cambrian explosion of new ideas, and that's what makes this time so exciting. Is so many entrepreneurs around the world looking at how do we transform the way we move around on a daily basis with air travel. So here's one of the propulsion blades, and so it's carbon fiber with a titanium root sleeve, and this combined with the very high specific torque motor is what makes the acoustic profile possible. You asked how slow do they spin? In cruise, it's as slow as 250 RPM.
250 RPM, no shit.
So
Wow.
we're like a many smaller GA airplanes, you're spinning at like 2,500 RPM.
Yeah.
This is spinning 10 times slower, and that's what makes it so that when you're in cruise and it's flying over, you don't hear the propellers at all. You just hear a whoosh.
Yeah. Well, I saw the how quiet it was when you compared it. We'll put a little thing on the bottom that compares yours to, I think it's 5 or 6 other aircraft, helicopters, a Cirrus and whatnot. I will tell you though, this right now is probably less than a kilo, so less than 2 pounds. I'm really impressed. People have shown me their ideas on what to do with props in general, and I don't know how you did it, but well, basically you've got the lower speed, so you can get rid of a lot of the mass that you have to have in order to withstand things.
So this is a titanium part which we print here. This is part of our one of our cooling manifolds, and as you can see, you're able to build a part that's incredibly
complex. Wowzers. Okay, so this is using additive manufacturing. Titanium is one of my absolute favorites for 3D manufacturing and or additive manufacturing. And this has just come out beautifully. This is the only way that you could possibly do something like you couldn't possibly cast it. If you were going to be welding this together, it'd take you forever, and it costs a fortune, and it would be hugely heavy. So I'm very intrigued by the elegant. I love elegant designs, and the elegant design then transformed into an elegant way of manufacturing, and this is just spectacular.
Control surface actuator.
Yeah. A lot of machining. That's for sure. Wowzers. Yeah, these are like you've got them in a display case for a good reason. I mean, they definitely look spectacular. Yeah, and I like the way that you've when companies usually get involved in manufacturing and whatnot, they look at the function, but they don't look at the elegance that you're going to need in order to make things work. And if you have a look here, you can see that there's 2 or 3 risers or ribs, whatever you want to call them, in here to give you the strength, but it's hollow to give you the lightness that you need in order to make things happen, because vertical takeoff eats up a tremendous amount of power. So having something that's been designed like that is the only way really you can make everything work. You have to be looking for every gram of weight savings. So
absolutely,
very impressive.
So let's go over and take a look at the airplane assembly line.
Great.
So this is our final assembly area, where once the airframes are assembled and painted and tested, they come in here, and all the components get put inside. So we have as we just saw there, and you'll see more when you see the facility in San Carlos, all the components we developed are really the heart of what makes this possible. Right. Very high specific torque motors, very light actuators. We design and build all of the power electronics and control systems that go in the aircraft, the switches and all the communication systems, the avionics, and that enables us to build a really next generation aircraft where all the systems are optimally tailored to work together. And you mentioned how challenging it is to build vertical takeoff and landing aircraft. Right. That is because you need all of the systems working in perfect harmony. And by building a vertically integrated company, a next generation aviation company, we're able to build aircraft with capabilities from an acoustic standpoint, from an emission standpoint, from a safety standpoint that really weren't possible before. And so that's what's really exciting here.
Well, I've always been even when it was unpopular, I've been a fan of vertical integration. I feel that as soon as you've got somebody coming in, usually a very expensive consultant, telling you that you've got a core competency, you have to go. As soon as you hear that, you know you're on the path to destruction. So the vertical integration stuff is actually a good example with Boeing. They moved from vertical integration to core competency. What we have to do, and they, doors fall off and stuff like that. It's very uncomfortable. So I'm very impressed. So you're making your own circuit, because that's usually the thing that people stop. Do you make your own circuit boards then as well?
So
or populate your own circuit?
We design all of our electronic systems, and then when you're up in San Carlos, you'll see all of those systems getting put together.
So how long does it taking now for a build?
We're still a bit.
I mean, in days. What are you shooting at?
We're still over a month. Again, by the end of the year, our goal is to be able to build one aircraft worth of parts a month. A month.
So one a month. And so who's going to be the first recipient of your?
Well, so we've already delivered the first aircraft to the first one that came off this line to Edwards Air Force Base. And
is that for testing, validation? Yeah,
exactly. And then we'll be delivering additional aircraft. We announced that we have another aircraft going to Edwards, as well as two going to MacDill in Tampa, in Florida. Oh, yeah. And so really excited about the opportunities on that front too.
Wow, that is cool. So the government is basically your first customer. What about commercial customers? How long before we see I can get a plane ride from Detroit Metro to downtown Detroit?
Well, Detroit's a fantastic example because we have our partnership with Delta, and Detroit is a critical hub for Delta.
It's number 3 on the list, and I can understand LA and New York. Okay, fine, but I will tell you that there's no easy connection. There's no train. There's no trolley. There's no nothing. You take a cab or an Uber to get to downtown Detroit. So this is, to me, this is a gold mine. You'll have to have about 100 of these things where people need to get downtown like right now, and they don't want to take 94. So I'm very excited to see what you're going to do there. Yeah,
absolutely.
Yeah. So how long before Delta starts getting some of their planes? So
with Delta, we are working on building the vertiport infrastructure for JFK, LaGuardia, and LAX. So that's we're working through the permitting process on that. Yeah. And as soon as those takeoff and landing locations get built, we'll be able to start service. The key piece is having takeoff and landing location that's directly connected to the terminal. Yeah. Delta's invested $7 billion into new terminal infrastructure, and being able to deliver customers directly to those terminals and make it as seamless as possible to get from a Joby flight onto a Delta flight, or from a Delta flight onto a Joby flight, and saving customers time, because that's what this is all about, is making delivering a magical experience.
Absolutely. Basically, nowadays, anyways, time has become even more valuable than the old adage, time is money. And now it's time is everything. Nobody can buy back a second for $1 billion. So, and seconds count in today's world. So this, I think, is just coming along at the absolute perfect time. Okay, so here we are in the cutting line. That's what's going on in back of me. So why don't we describe a little bit about this material and what's going on?
Yeah, so this is what the aircraft starts as. It's a pre-preg carbon fiber from Toray, which is one of the world's leading suppliers of high-performance carbon fiber. And it has a plastic sheet that's on both sides of it for protection. It comes on a big roll, and then this machine here is called a ply cutter, and it robotically cuts out the parts, and then once they're cut out, they get labeled, and so the machine automatically labels them, and then they get kitted, and then those kits go to the layup room, and we'll go there next and see the technicians laying up the parts.
Yeah, yeah. So we were just talking about the offal, the stuff that goes away. It's kind of like scraps. And we were just talking. One of the things that BMW on the i3 did was to take the scraps and figure out how to utilize the scraps so that they could make non-structural types of components out of what was left over. Because it's very difficult to turn this into something else.
That's exactly right. And that's one of the other pieces that we'll see is the AFP robots, automated fiber replacement robots. And one of the beauties of them, not only is it more automated, but it also has dramatically less scrap.
Yeah. So why don't we give me a little explanation of what's going on here with the placement machine?
Yeah. So this is our AFP automated fiber placement robot. We have two of them. This one is laying up a wing skin, and so it is applying the carbon fiber toes directly to the part, and because it's automated, it's very, very precise in the way it places the fibers, and it has dramatically lower waste. So it's laying individual fiber toes down onto the part, and in a very, very precise way.
So after the toes are put in place, what happens then?
So then the parts gets bagged and put in the autoclave and cured. So once the composite parts have been laid up, they go in the autoclave, and they are cured at high temperature and high pressure. And then when the parts come out, they get debagged and then demolded, and then the molds are prepped to make the next set of parts. So the autoclave gives us extremely high compaction and really high part quality, very consistent performance. And so that's what you see here.
Well, that is a very big autoclave. I got to tell you, I was when looking at the door and whatnot, I was very surprised. So, but you've got, you're just right at the beginning of the production operations and whatnot. Are you going to use any more? Are you going to need any more of these things?
Yeah, so we'll need a bunch of autoclaves. So here you see we've got 3 autoclaves of different sizes here. Yeah. This again is our pilot manufacturing line. As we scale it up, we'll have multiple autoclaves to keep up with the production, even when we're running all the shifts.
So are you looking for those autoclaves like right away, or are you?
Yeah, it's a progressive scaling. So we're a very opportunistic company where we, if we can get amazing deals on equipment, we'll purchase it.
Yes.
But also, when you buy secondhand equipment, it allows you to shorten the lead times. Some of these assets have multi-year lead times
Yeah.
on when you're looking at
Yeah.
building new ones. Always
So-
always looking for
Yeah.
good deals. This is where we take all the components of the aircraft, the propulsion stations, the batteries, the communication systems, the flight computers, the actuators, all the systems on the aircraft. We put them in the lab and we run them all. And so we've got a cockpit over here. So the components think they're flying. All the software is the same. And we're able to test lots of abnormal conditions, lots of failure modes. This lab is designed so that we can exercise the plane very quickly in rapid succession, go through one failure mode after another.
I'm impressed all the way around. I don't have enough words to really express how grateful I am for letting us come to see you. I'm telling you what, you've got a winner. And I don't say that very often, not on camera anyway. I'm really impressed. I really am.
Thank you so much.
Thank you.
So when you go up to see the team at 980, I think it's important to lay a little bit of the groundwork for what you're going to see. You're going to see where they build the batteries, the motors, the actuators, the flight computers, the heart that goes into making our aircraft possible.
Mm-hmm.
And the foundation that was built on was an incredible number of really brilliant engineers, some of which were early in the development at Tesla, both on the battery systems and the propulsion systems.
Yeah.
And so Jon Wagner, who I think you'll get a chance to meet, is he led the battery team at Tesla for many years. And before that, back in the late 90s, he and I built a robotics company together. So then we built the robotics company, and then he went off and joined a friend, JB Straubel, at Tesla, and then came back and now leads Powertrain here at Joby. And so I think you'll have a really good time learning and talking to him and seeing the technology that goes into and kind of the core and the heart of the plane.
I'm sure I'll have a good time, but I doubt if it'll beat this. I mean it sincerely. Thank you so much.
Thank you so much.
Thank you.
Really an honor to get a chance to spend some time with you.
The honor is mine, sir. I'm really impressed. So anyways, let's go over to the next facility and let's see what the heart and soul looks like. Hey everybody, we're at the next facility, and right now, Jon is going to give us a little bit of background. First, your background, and then we're going to go in and start looking at powertrain, electronics, and all the fun stuff that you can't see, but really makes everything happen. That good?
Yeah, very cool.
Cool. Yeah.
My name is Jon Wagner, and I run the design organization here for, as Sandy said, Powertrain and Electronics. And really, that's everything in the plane that has electrons flowing. So we're talking about the battery pack, we're talking about the motors, the power electronics, all that power distribution, the wiring harnesses, and of course the compute systems that make it all go.
So we've had a chance to have a look at your motor.
So if we look at the motor, this is in cruise orientation right now. On this far side from the camera, we'd have the propeller system. And in fact, it mounts directly to the rotating portion of this, the rotor. On the back side, what we're seeing is actually the thermal management system. So we've got the inverter already integrated. That's sitting inside this area. On the back of the inverter, we have the cooling pump. That's a dual redundant cooling pump, and that circulates the coolant from the motor to the inverter to the radiator in a closed loop. That pump also spins a fan. So essentially we're drawing the air. It actually comes in through the sides and out through the radiator. And so this is all a self-contained unit with all of the control and processing and power electronics. Essentially, we just connect up the battery terminals for the 2 different battery packs that power this, and we connect up the communication lines. And then this controls the entire propulsion system.
Now, the one advantage you do have is once you're up in the air, it's going to be a lot cooler than
That's right.
than on the deck. So if we look at this, this would be, I'm assuming, designed for like a Phoenix test where you're stuck on the runway for hours or whatever.
Yep.
Yeah.
Yeah. Actually, it's an interesting challenge to make this electric airplane because we've got the takeoff portion and the landing portion, which is much higher power than the cruise portion. What's nice for batteries, of course, those portions are very short. So we're really just using a small amount of energy to get up in the air. And then that's the benefit of a wing. From there, we're using the wing for the lift. So really the challenges have to do with when you're near the ground. That's where you have a lot of power, typically have hot air. And so this unit's developed and tested to the highest temperatures we find on Earth.
No. Oh, that's a Death Valley test.
Exactly.
Not a.
Yeah, we talk about 50 degrees Celsius, and we're more and more we're seeing that as an environment that people live in. So this system has to be able to manage its temperature on the ground in hot sun, be able to take off with full power under those conditions, and keep itself cool. So here we're showing the battery module. Actually, it's on its production cart. This is in the final stages of production. It's got some fixture around it, but essentially this here is the battery module that houses the energy storage. Now, on the plane, there's 28 of these. And we've selected a modular architecture specifically for its safety benefits, as well as manufacturing and maintenance benefits. So 7 of these make a battery pack. And on the plane, we have 4 battery packs. Those are located up in the wing and then in the forward nacelles. So this morning when you saw the plane, you probably saw where those batteries reside.
Well, we didn't see where they would, we weren't told where they resided, but I knew one thing, it wasn't in a cockpit.
Right.
So,
So
I was pretty happy about I'm a big fan of Space Claim, smart Space Claim, and cabins are not the spot that I want to see inverters or battery packs and whatnot. They should be somewhere else. So I like this idea. This looks a lot like the strategy that BMW initially started out with the i3. The only difference is yours looks like a, I could be wrong, but it looks like a fully machined, maybe not, when I saw the back.
Mostly machined. There's also some sheet metal parts, but it's all titanium. So that's what you won't find in the automotive battery system. And the titanium is there actually surrounding all of the battery cells to make a complete containment for any kind of emergency or failure. So the titanium has really good lightweight strength properties and also very good high temperature properties. So essentially what we proved to the Federal Aviation Administration and indeed ourselves is that we can withstand any kind of battery failure. And so you can imagine all the different failures we list that could occur, either electrical failures or other types, and we have to maintain throughout all of that a safe continued flight and landing. And so that's the contract we sort of sign with the FAA and of course with our customers, that we're going to deliver a safe landing. And we do that through a very extensive series of tests where we test every one of those failures.
Let's just talk about how that works with the open case.
Yeah, so we talked a little bit about the titanium shell here and why we do that. This is a sample of the shell, and you can feel how lightweight that is.
It's nothing there.
And titanium's incredibly strong and stiff, but what we do is we fully enclose the batteries. And this is missing its closure panel just to show you what it looks like. But as you can imagine, we couldn't get the battery cells in there after we put this together. So what we do is we assemble the entire module and then we
build
build the box around it
Yeah,
and do a weld that
Yeah.
seals hermetically around the entire module.
right.
And so,
So that's what I was just going to point out.
yeah,
If you look down here, you can see the laser weld going all the way around.
right.
And I've talked a lot about laser welding. It's my all-time favorite. A lot of people think that I have like some kind of contract with Trump or something, Trump lasers. But really and truly, the longer you get around manufacturing, the more viable laser welding is, especially when you're looking at something as light as this, and something that has to be incredibly strong. There's a lot of power inside these batteries, and you have to contain that if you have an event. And this will do the job because it's titanium, and because really and truly, I can count on that weld all day long.
So here we have the charging handle. So if you look closely, what you've got here is the electrical connections to charge 2 battery packs. So we've got positive and negative and positive and negative. And then here you've got dry connect liquid coolant fittings. So essentially what we're doing with this is you come up under the wing, and there's actually the cable is connected here, but this connects up into the wing. And then the way this works is that this handle allows you to essentially engage those connections. So we've got a latch here that comes up and will hold it, so you're not really holding the weight of this. And then when you rotate the wheel, you're engaging those connections. So this is the charging interface we've designed for the airplane, and we've made this public because we believe for all of the airplanes that are going to be electric, you've got to have a way to charge the batteries. You're typically going to have more than one battery, and you've got to have a way to do on-the-ground cooling as well.
Well, the good thing about that is that we don't have to go down the path that we used to have, the SAE thing, which everybody on the planet thought that had to have been designed by a second-year college student, and then we all had to switch over to the Tesla unit, which made things easy peasy. So what are we looking at? Is this 800 or 400 volts?
So this is an 800 volt. Technically, the standard is to 1,000 volts.
Wow.
Our aircraft doesn't go all the way up to 1,000
Yeah.
volts, but the charge infrastructure can go to 1,000 volts, and that's what the standard says. So it would be 2 separate battery chargers, each up to 1,000 volts.
Yeah.
And then on our airplane, as I talked about, since we have 4 battery packs, you actually have one connection under the left wing and one connection under the right wing.
So how long would it take to currently charge your battery system utilizing 2 of these units then?
Yeah, so that all depends on the length of the flight, but
Well,
essentially
from 20 to 80 or something.
Yeah,
like
exactly. What we're talking about is we've done extensive ground studies for passengers. How long does it take to actually get people off the plane, brief the next people, get them in, seat belts, luggage, all of the different things we're doing. And essentially the target that's given to our battery team is for short flights, we want to charge as quickly as it takes to get people on and off the plane. Now, as you start to get into the longer flights, there's a little bit more time on the ground, but we're talking minutes.
So what is the force required to snap that in? So we look at how, percentile of people that can do the job and whatnot. So what would the clamp, how many?
I'm glad you asked. I mean, and you can see this big, what looks like a steering wheel, and that's exactly what this is for. So essentially, what you can see is, actually, if you look from here, as you rotate the wheel, it brings up these contacts. And this was really an important thing because at the end of the day, lifting this with the weight of the cables and everything is very reasonable prospect. We're talking about under 20 kilograms, something like 15. Yeah. So this is not super lightweight, but it's very reasonable to lift this up and engage it. But unfortunately, the contact force for both the coolant connections, to seal them, is quite high. And so this is why we have this leverage for the final engagement. So you lift it, you latch it in place. Now it can be hanging, you can even be hands off. And then as you rotate, you're going to get the full connection. And our bodies are actually quite good at applying that kind of a torque.
Right.
Essentially what we're looking at here is the main propulsion dynamometer. And at the company we have 5 of these. This one we use for the research and development aspects where we're doing over torque, over speed, those kinds of excess tests. And what you can see here is a very large blue industrial motor. That's connected with its shaft through a big coupling system and a torque sensing system to the main propulsion motor. So the main propulsion motor is just this piece of it here. Yeah. And then essentially we drive that propulsion motor as if it was flying, and we put back torque on the system as if that was a propeller. Mm-hmm. And then along the wall you see these very large power electronics cabinets, and what's happening there is on one side we're simulating a battery, and on the other side we're driving this blue motor, and a lot of that power just recirculates essentially. Right. Yeah. So if we open this up, I'll show you. This is an elastomeric coupling right here. Right. And so this would be what fails. If anything's going to fail, we'll shear that right off. And essentially this also decouples any sort of stress that might be flowing through there. So this dynamometer that we have here was designed entirely by Joby engineers. Really? And the reason we did that is because we knew we were going to need a lot of them. So if you look on the other side, if you turn the camera to the other side, you'll see this is a very similar dynamometer, but you notice it's painted white on the bottom. And it's a small difference, but the key significance here is that this is for manufacturing. So every unit we build comes on here and gets about 2 hours of testing before it ships out of the factory, so that we ensure we've tested every function. Now this is for research and development, and like I talked about, and so we've got a convention where our blue equipment is for testing and our white equipment is for manufacturing. Now furthermore, down in Marina where you were this morning, there's 3 more of these dynamometers, and they're in what's called our Iron Bird. The Iron Bird is essentially a layout of all the components of the plane bolted to the ground. And we can virtually fly that plane, and the motor will be speeding up, slowing down, applying torque, and the pilot will be in the simulator with the controls. And we can study all the failure modes or all of any new software release. We can study what the behaviors are.
Well, John, I thank you very much for giving me that wonderful little tour. I am delighted that we made the trip out here to California to have a look at your company, collectively your company, and this has been brilliant. So I don't know how much more I can thank you, but thank you. Thanks, John.
My pleasure.
Thank you. This was great.
Thank you.
Thank you. And thank you for watching, and keep watching because there's going to be more to come, I'm sure. Thank you. Bye.